Let's talk about the definite integral. Jump right into the definition. Let f of x be a defined function on the closed interval a to b. The definite integral of f over a to b is the limit of the Riemann sum summation k equals 1 to n of f of ck times delta xk, provided the limit exists. This is the Riemann sum that we defined in the last video. And so what we talked about then was this Riemann sum is an approximation of the area under a curve, and that we could get an exact area as we took the limit of the Riemann sum as the partitions, the norm of the partition went to 0, or as the number of rectangles went to infinity. And so now all we're doing is we're defining that limit of the Riemann sum to be a very explicit thing. It is the definite integral. And the way we write that definite integral, it's the integration symbol that we've seen before, the integral sign, from a to b. So the only difference from the definite to the indefinite in terms of the visual is that we have now a little a written on the bottom of the integral symbol and a b written above. We still have the function or the integrand inside the integral symbol, and we have that dx differential. And now it's a little bit more clear why we have that differential there. Because what we see is this definite integral, and really any integral, is just an area under a curve. And that's what we're stating here. The area under the curve, y equals f of x over the integral a to b, over the interval a to b, is a equals the integral a to b f of x dx. An integral is just an area under a curve, as we define in the Riemann sum. And so if we think about what's required for an area under a curve, we need a height, and we also need a width. And that dx is replacing the delta x from before. Remember, the differential dx is saying what is the measure of the change in the x, and then this is the height. And so by adding all those heights times widths together, we are finding an area, and that's what the definite integral is. That's the basic of it. So let's just do a couple problems with this definite integral right now. And for the time being, we have not tied this to the definite. I know I've the indefinite. I've referenced it a couple times, and I've referenced that we've seen in the past, but I don't have anything explicitly tying the definite to the indefinite integral right now, other than they kind of look the same. So let's find the integral from 1 to 2 of 2x dx. So I'd love to just be able to treat this like I did the indefinite integral, but the problem is we just don't know how to do that yet. We haven't made that connection, and so we have to treat this thing as some sort of Riemann sum or some sort of area. And remember the Riemann sum example we did, that was a relatively simple one. It started at 0 and is still kind of tedious. It's a little bit of a pain and very theoretical. And I'd like to avoid that if possible. Now we can always go back and find that Riemann sum, but let's think about it in terms of the area, because that's another good way to think about definite integral. We know that this is just a line passing through 0, 0, and we want to know the area between 1 and 2. So we're looking for the area of this shape. Now, because this is a straight line, and it is not a curve, it is a straight line, we can just go ahead and find the area under it as we would a rectangle, or maybe even smarter, a trapezoid. This shape is a trapezoid. So remember how to find the area of a trapezoid. It is 1/2 base 1 plus base 2 times the height. Now, I know we've been calling this width here, but the height has got to be the consistent element. The bases are the things that are changing, so this would be base 1, and this would be base 2. So we need to find each of these elements. Let's start with the height because it's relatively easy. The height is just the delta x, or in this case, 2 minus 1, or 1. Now we're going to find base 1. Well, the base 1 is the function value at 1, and the function being this 2 to the x integrand. So base 1 would be equal to 2 times 1, which is 2, and base 2 would be equal to 2 times the 2, which is equal to 4. And so we have all the pieces we need now just to put it together. And so we will have 1/2 2 plus 4 times 1, 2 plus 4 is 6, and half of that is 3. And that would be the area. More importantly, what we're asked for, that is the area, that is our definite integral. We now know how to find that amount. We know how to find the definite integral, not because we're tying it to antiderivatives yet, but because we understand that it is the same as the area under the curve. We're looking for this area in here. As I said, another way to approach this problem, if you weren't as comfortable with trapezoids, could have turned it into a rectangle and a triangle. And so we would know the area of both of those shapes as well. The trapezoid's definitely a little bit faster. Let's do one more example. Let's find the definite integral from 0 to 3 of the square root of 9 minus x squared. Now, this shape, not as comfortable with. I know it's some sort of curve. Not sure exactly what it looks like. And I definitely don't know how to find the area under a curve. That's the whole problem in us doing all of this work, right? This is the whole reason we're studying the Riemann sum and turning it into the integral. So again, we need a dx on there, so make sure I don't forget the dx. I want to make sure I didn't forget it above. I'm good there. Needs a dx because we have to have that with element to it. We always have to have a dx on our integrals. But I don't know how to relate this to an antiderivative yet. And honestly, this is a very challenging problem to integrate even when we do know how to relate to an antiderivative. So this one will always be easier to relate to a curve. So let's think about what we have right now. We have a function y is equal to 9 minus x squared. Square root of 9 minus x squared. Let me do a little rearranging. I'm not quite sure what this looks like, and I'm just going to do a little tinkering. I'm going to square both sides. And I see I have an x squared and a y squared. I'm going to get those x squareds and y squareds to the same side. And lo and behold, the shape that I have, we should recognize this as a circle with a radius of 3. And so anytime we notice that we have the square root of this perfect squared minus an x perfect square, that is really a circle hidden there. That's part of a circle. It's not the full thing, though. Well, for one thing, we're only looking at this circle from 0 to 3. And the other thing to keep in mind is if we were to go back the other direction, right here, if we were to take the square root, we'd have to put a plus or minus in front. We never had that minus in front. We only had the plus, which means to begin with, we only had the upper half of the circle. We never had the lower half. And then on top of that, we only want to integrate from 0 to 3, so we only are really looking at this portion of the circle. Well, luckily enough, we know how to find the area of a circle. The area of a circle is pi r squared. And now that we recognize its shape, we know that it's a fourth of that circle. And so we are going to find the area of a circle with a radius of 3. That would be 9 pi over 4. And that would be our definite integral. So at this point, we have to rely on being able to draw out the shape and find the area under it, or we would also be able to go back and actually find that Riemann sum, but that's a little bit more work than I'd rather do. I'd rather just view it in terms of an area. As long as we can do that, it's not too hard to find these shapes. Now, everything I've done so far has been positive, and here's kind of the interesting thing with an integral that's not true of areas. Areas we always say are positive, but with our integrals take into consideration positives and negatives. So let me change this first problem a little bit, the 2x. Let's say this time we have a negative 2x, and we're still going from the 1 to the 2. Well, there's a couple of different ways I could do this. We have rules for integrals that say we could pull that negative to the front, and then we're back to the same answer that we had from before. We would just get the answer of negative, and I think it was a 3, negative 3 this time. But negative's kind of strange because we thought these things were areas, but here's the thing, because that negative 2x is now going downwards, where is that area occurring between 1 and 3? Well, it's occurring underneath of the x-axis. Anytime things are occurring under the x-axis, that's going to give us a negative integral. So we do need to pay attention to negatives. Even though we can view these things in terms of areas, they're areas with signs, essentially. They are almost the vector form of an area in that the direction or where that area is located. Another thing to consider if we had had the integral from 2 to 1 of 2x dx, well, that's kind of an awkward area. That means we're somehow backtracking along that line. We're going from here back to here. And so yes, the area would be positive, but if we're talking about the integral, because we're going backwards, this kind of awkward layout, remember we have the ability to switch the bounds of integration. That would be a lot more comfortable for us to find. And this is another example where we're going to get a negative value for that definite integral. If we're traveling backwards along a line, if our x's are going backwards, same way as if where I said I'm going backwards 5 steps, I'm going -5. Here we're going backwards in x direction. That's going to give us a negative result for our area. So we can find these definite integrals just using areas, but we do need to be aware that their sign now matters too.